When a crane lifts thousands of pounds of raw material into the air, the physical tension is absolute. Gravity pulls down, the cables pull up, and the machine in the middle absorbs every ounce of that opposing force. At these weights, mechanical failure is often instantaneous and absolute. Depending on which component yields first, the disaster takes one of three specific forms. The boom can buckle, internal mechanisms can slip, or the machine can tip over entirely. To prevent this, engineers rely on IS 14470, an Indian standard identical to ISO 4310. It prescribes a testing regime designed to deliberately provoke each failure mode under controlled conditions. We are going to look at exactly how inspectors verify the structural yield limits of the steel, test the endurance of moving mechanisms, and calculate exact tipping thresholds using coordinate geometry. Standardizing these testing limits provides the measurable boundary between a safe lift and a mechanical collapse. Before any load is attached to a hook, inspectors establish an absolute baseline by verifying conformity to specifications. This verifies that the physical machine operates exactly as designed. Inspectors measure the total mass of the crane, the maximum load lifting height, and the full range of operating speeds, including slewing, crab traversing, and precision load lowering. Once those operational metrics are verified, the process moves to a comprehensive visual inspection. The standard requires an evaluation of all vital components, wire ropes, structural connections, and electrical safety devices like limit switches. This is conducted without dismantling the machine to reflect its actual service condition. These preliminary checks confirm the machine matches its engineering blueprints, setting the stage for physical stress testing. Physical load testing begins with Phase 1, the static test. The purpose of this phase is to demonstrate the structural integrity of the metal framing and its load-bearing connections. To test these limits, the standard requires a test load exactly 1.25 times the rated capacity, designated as P. For mobile cranes, P includes everything suspended from the hoisting mechanism, payload, hook assembly, and all rigging attachments. The protocol is strictly controlled. The load is built up progressively, then lifted between 100 and 200 millimeters off the ground. The weight remains suspended, completely static, for a minimum of 10 minutes. The crane passes only if there are no visible cracks or permanent deformations. Inspectors specifically check for paint flaking at the joints, which indicates the underlying metal has reached its yield point and stretched. By pushing the metal structure to 125% of its rated capacity, the static test establishes a physical safety buffer for every lift performed during normal operation. After verifying the structure, the focus shifts to the machine's internal systems for Phase 2, the dynamic test. Dynamic tests are conducted to verify the functioning of the crane's moving mechanisms and its braking systems. For this phase, the test load is reduced from 1.25 P down to 1.1 P. This lower multiplier is a matter of engineering logic. Subjecting moving parts to a 25% overload during active operation could cause artificial wear on gears and bearings that are otherwise safe for their intended duty cycles. During the test, the operator runs the crane through repeated starting and stopping for every motion. This continues for at least 1 hour to simulate a full work cycle. The most demanding part of this sequence is the mid-air start. The crane must stop a descending load, hold it, and then resume the lift. The standard requires that there be no back running or slipping of the load when the gears engage during this maneuver. While static testing confirms the frame won't break, dynamic testing verifies the machine can safely arrest and control the kinematic forces it generates. The final phase for mobile cranes is the most mathematically complex, the stability test. The goal is to determine the exact point where the weight on the hook would cause the entire machine to tip over. Stability is a moving target. As telescoping jibs and secondary fly jibs extend, they shift the crane's center of gravity and change the leverage exerted on the chassis. To account for these variables, the standard uses a specific formula to determine the stability test load, 1.25 P plus 0.1 Fi. We can map the components of this equation directly onto the physical geometry of the crane. Capital G is the weight of the main jib, and lowercase g is the weight of the fly jib. The radii from the axis of rotation to the jib heads are designated as J and K. Radii M and N plot the exact centers of gravity, where the mass of those metal arms is concentrated along the horizontal axis. The variable Fi reduces these weights and distances into a single mathematical force applied at the lifting head. When lifting from the main jib, we calculate state F1. This is the jib's mass multiplied by its center of gravity radius divided by total jib radius. Lifting from the fly jib requires the more complex state F2, which incorporates the masses and radii of both jib sections simultaneously. If the main jib is excessively heavy, the standard allows for stability to be verified by these calculations alone, as a physical lift would be too dangerous for the fly jib structure. This derivation transforms a physical machine into a balance of geometric moments, ensuring it stays planted even in its most vulnerable configurations. The testing architecture of ISO 4310 functions as a tiered verification model. The effectiveness of the standard lies in the differential between the 1.25p static requirement and the 1.1p dynamic requirement. This gap allows engineers to verify the steel frame handles extreme peak loads, while moving mechanisms remain undamaged during certification. Adding the stability formulas accounts for the shifting center of mass, completing the machine's safety profile. This international standard codifies applied physics into a repeatable safety protocol. When thousands of tons of material are suspended in the air, safety is the result of this rigorous, uncompromising isolation of every possible failure point.